All right, welcome to the podcast of Transformers More Than Meets the Grid. This is chapter 14 from Principles of Electric Circuits, Conventional Current. My name is Professor Vasquez. Welcome back to Magnetic Minds, where current flows and concepts connect. Today we begin chapter 14 of Principles of Electric Circuits, Conventional Current, and it's all about a truly powerful component, both literally and conceptually. Transformers. No, not the robots. Though these devices do perform some serious energy conversion, the transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. It's one of the most elegant applications of everything we've covered so far. Magnetic fields, AC sine waves, mutual induction. Transformers are everywhere, from power grids to phone chargers, from audio amplifiers to isolation systems in labs. Understanding how they work means understanding how we deliver power, scale voltage, and adapt energy to fit every electrical situation. In this chapter, we're going to cover the basic operations of a transformer, step up versus step down designs, turns ratio, voltage over current relationships, and efficiency, and how to calculate, analyze, and apply them in real-world circuits. So grab your core, wrap your coils, and let's energize this episode. So let's talk about mutual inductance, where magnetic fields meet electrical influence. To understand how transformers work, we have to start with a powerful phenomenon at the heart of electromagnetic theory, which is called mutual inductance. So here's the big idea. When the magnetic field of one coil changes, it can induce voltage in another nearby coil. And this process is called mutual inductance. It's symbolized by the letter L sub M. Right? In this diagram, we have two inductors, L sub 1, where the source coil with a changing current, and L sub 2 is that nearby coil where voltage is induced by L1's magnetic field. So when these coils are close together, that changing flux from L1 passes through L2, linking them magnetically. The more effectively they share this magnetic field, the greater the mutual inductance. Coils can either aid or oppose each other. If their magnetic fields reinforce one another, inductance increases. If their fields oppose, they can partially cancel out. That leads us to another key term, the coefficient of coupling. That's symbolized by the variable K. K ranges from 0 to 1. K being equal to 0 means the coils are not coupled at all, completely isolated. K equal to 1 means the coils are perfectly coupled, 100% of the magnetic field is shared. So most real-world transformers operate with K values near 1, but never exactly. Some magnetic flux is always lost. This interaction, energy transferred through magnetic fields, is the essence of how transformers transfer voltage from one circuit to another without direct electrical contact. All right, so we're looking at calculating magnetic coupling, the mutual inductance formula. We see that the mutual inductance is what links two coils magnetically. Let's look at how to calculate it. The formula for mutual inductance is L sub M, right? That's equal to K times the square root of the individual inductances, L sub 1 times L sub 2. The square root of L sub 1 times L sub 2, you see there on the slide. K is that coefficient of coupling, a value between 0 and 1 that describes how well the magnetic fields of the two coils are linked. L1 and L2, or L sub 1 and L sub 2, are the self-inductances of each coil, and they're measured in something called henries, denoted by the variable H. The square root of their product gives us a geometric mean, which is scaled by K. This equation gives you a numeric value of how much one coil's changing current will influence the other's voltage throughout mutual inductance. So what affects K? Several real-world factors. So the physical distance, the closer the coils, the better the coupling. The alignment, perfect axial alignment results in stronger coupling. Core material, coils wound on a common magnetic core like a transformer or like in transformers, they have a very high K. Shielding or misalignment, that can drop K significantly. And in transformers, the goal is to maximize K, ideally close to 1, so energy is as efficient as possible. So next time you see two coils interacting in a circuit, whether in a transformer, a wireless charger, or an audio crossover, you'll know the secret behind the signal. It's not just the current, it's the magnetic handshake between inductors. All right, moving on to the basic transformer, two coils, one mission. You've learned about mutual inductance, the engine behind magnetic coupling. Now let's build a machine around it, the basic transformer. At its heart, a transformer is incredibly simple. Two coils wound on a common core. And why a common core? Because it provides a controlled path for the magnetic field lines, maximizing mutual inductance and energy transfer. Let's look at the three types of core structures shown here. We have the air core transformer. Just two coils in space, no shared magnetic material, lightweight but weak coupling, a very, very low K. Used in radio frequency applications where magnetic loss is less critical. Then we have the ferrite core transformer. It uses a ferrite ceramic-based core. This is excellent for high frequency circuits like switch mode power supplies and RF transformers or radio frequency transformers. You have low losses at high frequency. Then you have the iron core transformers, most common for power applications. High magnetic permeability equals strong coupling. It's efficient at low frequencies like 50 to 60 hertz power systems. And to the right, we see a small power transformer. And the kind you might find in a wall adapter or an audio amplifier. So inside that, you'll see one coil called the primary, receives the input from the AC. And then the magnetic field flows through the core to the secondary coil, inducing a voltage. And that's it. No moving parts, no physical contact, just pure electromagnetic magic. Transformers step up or step down, provide isolation, and enable impedance matching across circuits. They're essentially critical for everything from power grids to something as simple as your microphones. Simple? Oh no, maybe something as everyday as your microphones. All right, let's jump into the turns ratio, or the concept of the turns ratio, how we scale voltage by design. Now that you know a transformer is built from two coils, let's answer a key question. How does a transformer know how much to step the voltage up or down? The answer lies in the turns ratio, a fundamental design parameter that determines how voltages relate between the primary and secondary windings. The turns ratio is defined as N is equal to capital N sub-secondary, meaning the number of turns on the secondary side, divided by the number of turns on the primary side, or N sub-prime. So N sub-secondary, again, number of secondary turns, and N sub-primary, the number of turns on the primary side. N just equals the turns ratio. And this ratio tells you how the transformer modifies voltage. If N is greater than 1, little n is greater than 1, the ratio, the transformer is a step up, so it increases voltage. If little n is less than 1, it's a step down transformer and it reduces voltage. So let's go ahead and look at this example. You have a transformer, it has 800 turns on the primary. It has a turns ratio of 0.25. And to find the number of secondary turns, we just use the formula where capital N sub secondary is equal to small n, which is the turns ratio, times the number of turns on the primary. So we plug in some numbers, 0.25 times 800, that'll give us 200 turns. So this transformer will output 1/4 of the voltage applied to the primary. That's useful when stepping down high voltages to safer, usable levels. Even though most real transformers don't have this ratio printed on them, it's a vital tool for understanding voltage transformation, impedance matching, current relationships, so which we'll cover soon. And the best part, the ratio also applies to the voltage and current equations that we'll be using in the next few slides. All right, let's go ahead and continue with the construction of one of these transformers, and let's look specifically at the winding direction, that hidden twist behind polarity. So far we've covered transformer cores, turns ratios, and coil interactions, but here's a twist, literally a twist. The direction of a coil's winding can affect the polarity of the voltage on the secondary side of a transformer. This matters because transformers don't just change voltage. They also determine the timing and direction of current flow between coils. So take a look at the slide here. On the left we see in-phase windings. Both the primary and secondary windings are wrapped in the same direction. As current rises in the primary, the voltage in the secondary rises as well. The result? The output waveform is in phase with the input. Hopefully I said that correctly. The output waveform is in phase with the input, right? And then on the right, the windings are out of phase. So one coil is wound in the opposite direction. The induced voltage now has reverse polarity. So the output waveform is 180 degrees out of phase with the input. This difference doesn't change the magnitude of the voltage, it just changes its polarity relative to the primary. And that can be crucial in push-pull amplifier configurations, which we'll learn about in a few courses down the road. Balanced signal transmission, timing sensitive circuits like oscillators or inverters. And notice that the dots on the diagrams, these indicate the terminals that are considered to be electrically equivalent in polarity. If both dots are on the same side, the windings are in phase. If the dots are on opposite sides, the windings are out of phase. So engineers use these dots when connecting transformers to ensure correct phase relationships across the systems. Now we've mentioned step up and step down transformers. What do we mean by this? We're controlling voltage with coil count. So at this point, you've seen how turns ratios controls voltage. Now let's label the two most common uses of a transformer. Step up, step down. Right? A step up transformer increases voltage. That means the secondary voltage is greater than the primary. And that also means that the turns ratio N is greater than 1. You'll find these in applications like high voltage transmission lines, CRTs, and in some audio preamps. The step down transformer reduces voltage. Here the secondary voltage is less than the primary, and the turns ratio there, N, is less than 1. So this is what you see in wall chargers, the ones that you use to maybe charge your phone, power adapters, distribution transformers that can take 14,000 volts down to 120 volts for homes. Those are large ones, not like the little ones you plug into the wall. Let's walk through the example on this slide. So you're given a primary voltage V sub prime, V sub PRI of 120 volts RMS or sub RMS. And the secondary voltage is 30 volts sub RMS. And that's a turns ratio of 4 to 1, right? 30 goes into 120 as 4 to 1. But wait, if the primary has 4 times more turns than the secondary, this is clearly a step down transformer. So let's go ahead and calculate a turns ratio now. So if I have N is equal to V sub secondary over V sub prime of 30 over 120, that'll give me 0.25. Right? So that means that matches the answer that's given as a 0.25 turns ratio, or 0.25 is 1/4 or 1 to 4 in terms of voltage step down. So here's your rule of thumb. Voltage ratio equals turns ratio. Step up, N greater than 1. Step down, N less than 1. And remember, current does the inverse. Higher voltage means lower current, and vice versa. So lower voltage means higher current. And that's going to be coming up in the next segment. All right, let's move on to another type of transformer, which is called an isolation transformer. And that's just breaking the connection without cutting the power. You've seen how transformers can step voltage up or down, but sometimes the goal isn't to change the voltage at all, or the current. Sometimes the goal is just isolation. That's where we introduce the isolation transformer. It looks just like the regular transformer, a special kind of transformer with a turns ratio of 1 to 1. Right? So what does that mean? The primary and secondary have the same number of turns. The output voltage equals the input voltage. But the two sides are electrically isolated because they're not making physical contact. The voltage is being induced from the primary to the secondary. Right? So you have no direct connection, no shared ground. Only the magnetic field is the link between them. And why is that useful? Because if it breaks the DC path while preserving the AC path, right? AC generates a changing magnetic field, so it transfers across. DC, on the other hand, doesn't change. No changing flux means no induced voltage on the secondary side. So this is incredibly valuable when you want to protect sensitive equipment from ground loops. Let's say you're servicing line-powered electronics. You need a safely reference for a circuit without creating a ground hazard. In the diagram, you can see you have 120 volts AC as the input. You have a 1-to-1 transformer and an output that's still 120 VAC, but now it's isolated from the source. There's no common ground. And that makes all the difference when you're working with mixed signal or industrial systems. So even though the voltage stays the same, the function of the transformer changes. The power conversion is no longer the issue. It's more about safety and integrity of the circuit. Safety for the technicians and safety for the users. Let's go into the next part, which is coupling transformers. And this is where you pass the signal and you block noise. So again, we've seen, just as a recap, we've seen how transformers can step voltage up, step voltage down, and we've also seen now how they can isolate circuits entirely. Now let's talk about another important application, which is signal coupling. This is where the coupling transformer shines. A coupling transformer isn't focused on changing voltage either. It's designed to transfer AC signals between amplifier stages. They also block DC components that could damage or distort the next circuit, and often shape the frequency response, acting like a filter. So let's take a look at the diagram. We've got two amplifier stages. Stage 1 sends out a signal that includes both AC and DC components. A coupling transformer is placed between the two stages. On the secondary side, only the AC voltage is passed through to stage 2. And why? Because DC doesn't produce a changing magnetic field, so it doesn't transfer through the transformer. This means the transformer acts like a DC block while still transferring the useful AC signal. You'll find coupling transformers in audio amplifiers where they isolate noise and preserve tone, radio frequency circuits where they pass only certain frequencies, modulation systems which help transfer power or data without direct electrical contact. The circuit might also include resonant components like capacitors that form bandpass filters that let only a select range of frequencies through. So while isolation transformers keep people safe, coupling transformers keeps signals clean, especially when transferring energy between sensitive stages. Current transformation. What goes up must come down. We've talked about how transformers change voltage based on the turns ratio. But what about current? Here's a key idea. Transformers don't add power, they redistribute it. Hopefully I said that correctly. Redistribute it. I mispronounced it so incorrectly. And so that means that if you step up the voltage, the current must step down, and vice versa. If you step down the voltage, the current steps up automatically. So let's look at the turns ratio equation for current, where N is equal to I sub prime divided by I sub secondary. Remember, use the formulas that we use in this course and in this book, because there are formulas that are IEEE standard formulas. Don't use something that you find on a web page that may not use this correct ratio. So when we're looking at it, N is the turns ratio, as always. I sub prime is the primary current. I sub secondary is a secondary current. That's not a big stretch there. Notice how this is the inverse of the voltage equation, where you have N, the turns ratio is equal to V sub secondary divided by V sub prime. So when voltage goes up, current goes down, keeping power roughly constant in an ideal transformer with no losses. Now, if you're trying to figure out where the root of this comes from, think of the power equation where voltage times current is equal to power. So power in is equal to power out. And so again, P is equal to I times V. And if voltage goes up, current must go down. If voltage goes down, current must go up. So you can have the same number for power on both input and output. Why does this matter? If you're using a step-up transformer to increase voltage, the device on the secondary side will draw less current. If you're stepping voltage down, the load must receive more current to maintain the same power level. This is especially critical in power distribution systems where stepping voltage up minimizes current and reduces the I squared R losses. In other words, I squared is I times R. And those are losses that we experience in circuits. Audio amplifiers and signal transformers where matching impedance also means matching current behavior. Just remember that voltage and current are inversely related in transformer operation. The product of voltage and current, which is power, stays roughly the same. And this balance is what makes transformers so effective and why you must consider both voltage and current when designing or analyzing them. So what's happening here is there's a great balancing act in transformers, a balancing act of power. So let's put everything together. Let's put voltage, current, and turns ratio together and how they all connect through the core concept of power. Right, here's the headline. In an ideal transformer, power in equals power out. That is just a universal constant law in the universe that power can neither be created nor destroyed, just changed, right? So power in the primary is equal to power in the secondary, or voltage in the primary times current in the primary is equal to voltage in the secondary times current in the secondary. So in other words, even if the transformer steps up the voltage, it must step down the current to keep the total power constant, neglecting any losses. This is what makes transformers efficient tools for energy transfer, not energy creation. The last equation on this slide shows the symmetry we've talked about. So V secondary over V primary is equal to I primary divided by I secondary. So if you look at this ratio, this directly reflects the turns ratio N. So every time you calculate voltage or current changes in a transformer, you're applying power in equals power out, or at least power in is approximately power out. This is very, very close. Again, not considering the power losses. Real transformers aren't perfectly efficient. No component is. They have core losses, copper losses, and sometimes leakage inductance. But power transformers, like those used on the grid, they're designed to operate very close to ideal at 60 Hz utility frequency. And the construction is optimized to pass AC power efficiently from source to load, with minimal loss and maximum reliability. So remember, voltage goes up, current must go down. Voltage goes down, current must go up for power to remain the same. So power stays balanced. That's the genius of transformer design. It moves energy across circuits without contact, without noise, and without wasting power when done right. So I shouldn't even say it's a transformer design. It's just the law of nature. It works that way. It can't work any other way. We couldn't create a transformer that has voltage and current to go up on the same side, and then voltage and current to go up on the same side, and voltage and current to go down on the other side. They have to be proportional. And finally, let's conclude this lecture with taps and options, customizing transformers for versatility. So far we've explored basic transformers, step up and step down designs, and power transfer. But what if you need more than one output, or want to support different input voltages with the same unit? That's where tapped and multi-winding transformers come into play. A tap is a connection made to an intermediate point on a transformer winding. It allows access to a partial voltage from the total winding. So in the left diagram, the secondary coil has a center tap. It creates two equal voltages, each half of the full secondary voltage. So for example, a 24 volt winding, the center tap gives you plus and minus 12 volts, useful in dual supply circuits like op-amp biasing. This makes the transformer more flexible, helps reduce the need for separate winding sets. It also lowers costs, but we're not going to talk about that in this course. We're more focused on design. On the right side, we see a transformer with multiple windings in the primary. Why would you want that? To allow for operation at different input voltages, like 120 volts or 240 volts. These configurations are common in power supplies for international equipment, audio gear, industrial control panels. Depending on how the windings are wired, in series or parallel, the transformer adjusts to match the incoming voltage. And the key takeaways here are: the taps let you access partial voltages, multiple windings provide multi-mode operation, and these features add versatility without requiring multiple transformer models. So next time you see a transformer with extra wires or label taps, you're not just looking at extra hardware, you're seeing a design optimized for adaptability. All right, let's go ahead and go through some key terms that we learned on this chapter. The first one is mutual inductance. I'm sorry, some of these we didn't actually cover in the slides, but may have talked about the concepts in previous lectures. Mutual inductance, the inductance between two separate coils, such as in a transformer. A transformer, an electrical device constructed of two or more coils, windings, that are electromagnetically coupled to each other to provide a transfer of power from one coil to another. Primary winding, the input winding of a transformer, also called primary. Secondary winding, the output winding of a transformer, also called secondary. And continuing on with the selected key terms, next one is magnetic coupling, the magnetic connection between two coils as a result of the changing magnetic flux lines of one coil cutting through the second coil. The turns ratio, the ratio of the turns in the secondary winding to the turns in the primary winding. The reflected resistance, the resistance of the secondary circuit reflected in the primary circuit. and impedance matching, a technique used to match a load resistance to a source resistance in order to achieve maximum transfer of power. As we go through this review quiz, go ahead and answer the question mentally, pause the video, answer it, think about it, and then continue the video because I will be giving you the answer immediately after I read the question. All right, so question 1. The measurement unit for the coefficient of coupling is A, the ohm, B, the watt, C, the meter, or D, dimensionless. Pause the video now. Okay, hopefully you're back. And the correct answer for number 1 is D. It's dimensionless. Question number 2. A step-up transformer refers to one in which what? A, the voltage across the secondary is higher than the primary. B, the current in the secondary is higher than the primary. C, the power to the load is higher than delivered to the primary. There's a typo in the publisher there. And D, all of the above. And while we're waiting, I don't think I can fix that typo. The question, pause, come back. And the answer for number 2 is A. The voltage across the secondary is higher than the primary. I'll fix that typo the minute I stop this recording. Question number 3. An isolation transformer does what? A, blocks both AC and DC. B, blocks AC but not DC. C, blocks DC but not AC, or D, passes both AC and DC. Go ahead and pause the video. All right, if you're back, the correct answer to this one is C. It blocks DC but not AC. Question number 4. If the current in the secondary is higher than in the primary, the transformer is a what? A step-up transformer. B, an isolation transformer. C, a step-down transformer, or D, not enough information to tell. Go ahead and pause the video. All right, hopefully you're back. And the answer for this one is C, a step-down transformer. Question number 5. An ideal transformer has what? A, no winding resistance. B, no eddy current loss. C, power out is equal to power in, or D, all of the above. Go ahead and pause the video. And hopefully you're back. 5 would be D, all of the above. Question number 6. Assume a step-down transformer is used between a source and a load. From the primary side, the load resistance will appear to be what? A, smaller, B, the same, or C, larger. Go ahead and pause the video. And hopefully you're back. And the answer to this one is C, larger. Next question. A transformer that can deliver more power to the load than it receives from the source is A, step-up type, B, a step-down type, C, an isolation type, or D, non-existent. Or E, we just won a Nobel Prize and we'll be rich. Pause the video. And the correct answer is D, it doesn't exist. Question number 8. A transformer that can deliver more power to the load than it receives from the source, very similar to the last question. Make the load appear to be the same as the source voltage. Make the load resistance appear to be the same as the source resistance. Make the load current appear to be the same as the source current. Provide more power to the load than is delivered from the source. Go ahead and pause the video. And the correct answer here is B. It makes the load resistance appear to be the same as the source resistance. Question number 9. A type of transformer that tends to not be ideal because it is designed for a good frequency response is a what? A, step-up type, B, step-down type, C, isolation type, or D, impedance matching type. Go ahead and pause the video. All right, hopefully you're back. And the correct answer for this one is D, impedance matching type. And the last question for this lecture is 10. A transformer that could be used for 120 volts or 240 volts operation is a what? A, multi-winding type, B, center tap type, C, isolation type, or D, all of the above? Go ahead and pause the video now. All right, hopefully you're back. The answer is A, a multiple winding type. And that concludes the self-assessment portion of this lecture. All right, here are the answers to the previous 10 questions. Go ahead and compare your answers, determine where you are correct and where you are incorrect with the questions. Make sure you understand why the answer you chose was incorrect and why the correct answer is correct. It's not enough to just know the right answer. It's also important to know why the wrong answers are the wrong answers as well, so you won't repeat those.